Okay, so what we looked at in the last video, let's just go through a recap. Again, we looked at the four major components. We assembled those four major components, built a PFD, and really kind of looked at what's happening in a big picture with this system. Now what I want to go do is let's build out our assumptions to make the base case. And really this base case is going to be, maybe a better term for it is the ideal case or the perfect case. Because what we're going to try and do is, we're going to try to make some good assumptions to try and figure out the most perfect cycle possible, okay? We're never going to be able to achieve this cycle, but we want to have this bench line to say, this is what perfect looks like, so we can measure our other cycles by that to say, how close to quote-unquote perfection are they? Are they an ideal cycle? Are they a perfect cycle? Or are they 85% of an ideal cycle? Okay? So that's one reason that we would do this. But the second reason is really the more, I guess, practical reason. So let's say before we were designing this process, and we're actually going to work through an example here in one of the later subsequent videos. Well, let's say we were looking at a refrigeration cycle to upgrade in our unit, because this new upgraded refrigeration cycle, maybe it had a bigger compressor, maybe it had a bigger condenser, but it was a more beefed up unit. It gave us more chilling capacity, it gave us more heat removal on this cold side. Well, in order to build that, in order to get that higher cooling capacity, for say, let's pretend for instance that we needed this higher cooling capacity to make the reactor run faster. Okay? How much energy now are we going to have to input on this compressor? Well, we could go through the whole detailed design every intricate detail of the compressor, the piping, the heat exchanger, the valve, the other heat exchanger, and we could go through that whole detailed process and waste everybody's time to come up and figure out that this isn't going to work. We're not going to save money because all the added production that we made in the reactor is going to be offset by the increased compressor cost. So it would be very nice to have a quick way to analyze this cycle, maybe against an ideal case, to say, listen, we can't get any better than this, right? So if anything, it's going to cost more energy to get us this cold. The point being is, I can do a quick calculation for this ideal cycle we're about to make and say, if it doesn't work for the ideal cycle, it's not going to work for any of them. So I don't need to waste my time detailing out all the intricacies of this cycle for something I could do in 5 minutes and go back to the business guys or go back to whoever proposed this idea and say, look, we got to come back to the drawing board because this isn't going to work. We're not going to make money doing this. Okay? So let's go through some assumptions that we're going to need to make in order to build our ideal cycle. And we're really going to walk away with 5 major assumptions. Most of the assumptions are going to be around the major pieces of equipment. So let's look at these. So I'm going to put up here ideal cycle assumptions. The first one's going to be around the expansion valve. I'm abbreviating this EV. And we're going to assume that the expansion valve is irreversible. It's frictionless. And it's adiabatic. Now, from classical thermodynamics, you should have an understanding of what irreversibility is, but let's just talk about it at a high level. Remember, we're going from pressure 4 to pressure 1 in a step, in a finite step. based on classical thermodynamics, that makes this an irreversible process, because remember, reversible processes increase or decrease by infinitesimally small amounts. So although in the real world there is no such thing as an irreversible process, or excuse me, a reversible process, remember the reversibility is this ideal, much like we're about to make an ideal cycle, this ideal concept of perfection. But we can approach this reversibility much closer than just a valve. We could put here a turbine, which would then be a Rankine cycle. We won't talk about why we won't put a turbine there, but know that you can, but it doesn't really give all that much payback. But in any case, because it happens, it's an irreversible step here. The second assumption revolves around our evaporator. And we're going to assume that that is isobaric. So what does that mean? That basically means that the pressure between state 1 and state 2 is the same. So we're going to assume that P1 equals P2. Because we're at equilibrium, what does that also mean? It also means that the temperature is the same. So T1 equals T2. The third assumption that we're going to make is around the compressor. And we're going to assume that the compressor is isentropic. Now you may be saying, there's no such thing as an isentropic compressor, Josh. You're right, there isn't. But again, what are we trying to build in this ideal model? Trying to build the best case. So in our best case, we're going to assume that this compressor is actually reversible, meaning that the entropy at state 3 is equal to the entropy at state 2 because the compressor is not imparting any entropy. It's isentropic. The fourth assumption that we will make is that the condenser is isobaric, just like the evaporator, right? So what does that mean? That means also that P3 is equal to P4. These pressures are equal. Very key to note. Remember how we said pressure here is equal to pressure there, and also the temperature here is equal to the temperature there. Remember how I said that's because they're still in equilibrium. We still have saturated vapor, and we have a vapor-liquid mixture. Not the case here. We have a superheated vapor going to a saturated liquid. So the temperature here does not necessarily equal the temperature here. The last assumption that we're going to make here in constructing our ideal cycle is the piping. We're going to assume that the piping is frictionless, meaning that it's not going to lose any energy as it flows through the piping. Once you get to fluid dynamics, you're going to realize, hey, that's impossible. I know. Again, we're trying to build the best case. So we're going to eliminate the friction here, even though in practicality, that's not going to happen. So you see that we're building this perfect standard that's not really achievable. So if you walk away from an evaluation that the perfect standard is not going to make you money, nothing else is going to work, okay? It's important. I'm drilling that home, but I want you to understand the importance there, because a lot of people miss that. The other assumption that's baked in here into this piping is that it's adiabatic. And all we're getting at on the adiabatic portion is that there's no heat transfer happening on these pipes. The only heat transfer that's happening is in the exchangers, okay? And so with these assumptions, we've just constrained the system to a point that we can go through and solve for how much work it takes to get this working fluid. We'd have to constrain the system further and say, what type of refrigerant are we going to use? And we'd also have to constrain the system and say, what's our hot temperature medium and what's our cold temperature medium? What do we want T1 to be and what do we want T4 to be, okay? But once we do that with our ideal assumptions, we can go through and solve to figure out how much work the compressor actually has to impart in the system, which is the important part of this cycle, because that's what we're going to pay for to run, is this compressor. Okay? So real quick, the next video we're going to look at the diagrams. I'll explain those a little bit more, but I want to recap what we just went over. Ideal cycle assumptions. Remember, we said that the expansion valve is irreversible. We can make it close to reversible if we were to put a turbine, but remember, we have a finite step change. It's frictionless, adiabatic, so it's not causing friction loss here, although once you get to fluid dynamics, you're going to say, that's not right. And then also we're assuming it's adiabatic, so it's not going to exchange energy with the surroundings. Again, all the piping, frictionless, adiabatic. Both of the exchangers, what we're assuming here, and again, once you look into heat transfer and fluid dynamics, you also say, Josh, that's kind of a bad assumption, because what's happening here between state 1 and state 2 and state 3 and state 4? Notice you have a phase change. Phase changes in exchangers normally have a decent pressure drop. You're right. But what's our purpose? Our purpose here is to give ourselves an ideal baseline. So it's going to work, okay? We're going to walk away with an ideal baseline, because the only thing that a pressure drop here is going to do is cause the compressor to work more, because it has more restriction, okay? We assume that the compressor is isentropic. In real life, that will not be the case, but for our ideal model, it's good. Because the only thing that's going to happen is now, in the real world, it's not going to be isentropic. It's going to be inputting work into other things other than pumping the fluid. So once we start working some examples here, a lot of these assumptions, you'll see how these assumptions help us constrain the system. In the next video, what we're going to look at are TS, or temperature entropy diagrams, and pressure enthalpy diagrams. Thank you.